so highlighted projects. So I'm going to show you projects from Karen Zito and Lynn Tien. Lynn's not on there. From Evan Anselatis, who's in the back row there and will be signing autographs at the end of the talk. Kathy Ferrara, who's from our biomedical engineering department, and Tara Nienda. And these are just examples. I just want to give you a little bit of a taste. So Karen's project, let's just jump right to this. What Karen is doing, along with Lynn Tien, is developing some calcium sensors. These are basically molecules that turn on and off in the presence of different kind of light, and can be inserted into neurons using a virus. And they can not just image the spines that I showed you earlier, but actually image very specific kinds of spines. So, for instance, this is an example of an image of glutamatergic spines. These are one of the kinds of neurotransmitters in the brain that communicates excitation. It's the way that one cell excites another. So, since we have at least one psychiatrist in the audience, Cap. It's possible. Oh, sorry, and Bob, at least two psychiatrists in the audience. It's possible to, Mike, 3, any more psychiatrists before I leave you out and insult you? That's the parietal cortex talking to the visual cortex, not quite right. So it's possible to actually then dissect out changes in the density of spines that hold synapses in different classes, including glutamatergic, serotonergic, GABAergic. So it takes that high-resolution 2-photon imaging that I talked to you about earlier and just takes it to absolutely the next level. And this will be done in animals initially in an epilepsy model. So as the circuits of epilepsy fire, this group will be able to image the changes in the glutamatergic connections of neurons that occurs and results in a miswired circuit that makes the epilepsy worse. And then ultimately it'll be able to be done in animals learning, recording from the circuitry that's involved in support of learning, so that we can see the cells that fire together, wire together, down to the level of the kind of synapses that they're using to talk to one another. I think Dr. Myers alluded early in his introduction to the fact that, we've relied a lot on drugs over the years to treat mental disorders, and the last 10 years has been pretty disappointing for those of us that rely on those drugs, because there really haven't been any new ones. And many of the companies that make drugs have stopped really doing research in the area of CNS. It's too risky, it's too expensive. And so, there is a sense of frustration that is in conflict with the reality that we've learned so much about how the brain works, and why can't we use it? And I think there's a growing awareness that actually we can. The brain isn't that far away. Actually, it's right in there. And it responds to the environment much more than you think. I mean, obviously, our senses are responding to the environment, and our brain is responding to our senses. But actually, it's possible to change the brain. What we've lacked up until the last decade or so is understanding the circuitry, understanding its dynamics, understanding how it works. But we know that now. So can't we use that knowledge to help some of these broken circuits? And I think the answer is it's becoming fairly clear that we can. So this is a technique called transcranial direct current stimulation, or TDCS. Has anybody heard of this? Yep. And if you haven't, does anybody not have YouTube? Just go to YouTube. Type in TDCS. You will see a 13-year-old kid show you how to build a TDCS rig out of a 12-volt battery and some electrode pads, and use it to improve his computer game skills. You will see it online. It's not actually a good idea that 12 and 13-year-old kids are building this rig, because we don't really know exactly how to make these systems work. They're out there. There's a lot of studies that have been done. So basically what this involves is putting a very small amount of electric current on the scalp. Typically 1 to 2 milliamps. Tiny, tiny, harmless. You get a little tingling if you get anything at all. And what people didn't realize, although they should have, because some stuff had been done maybe 40 or 50 years ago doing this, is that current doesn't just sit on your skull. It goes through your skull. It goes into your brain, and it actually travels down those columns, and it changes the excitability of neurons. So you can, if it's a cathodal current, it'll push the neurons further away from firing. If it's an anodal current, it'll push the neurons closer to firing. If you have somebody do a task and it generates an oscillation in a particular frequency, the intensity of that oscillation becomes increased. And that's exciting because it's through that neural activity that the circuits wire together and that you can establish normal patterns of connectivity in the brain. And so we know that under some circumstances you can improve the ability of somebody to perform on a particular cognitive task using this approach, but we don't really know what the parameters are. We don't know where we should stimulate. We don't know how. That's where the science is right now, is figuring all of that. The 12-year-olds and the 13-year-olds, they don't care. They just want to get better at the World of Warcraft. And there are quite a few companies actually that have decided they're not going to go the evidence-based FDA route. And you can go online and you can buy your TDCS stimulator for $200 or $300. It's much nicer than the 12-volt version. It's more like this. And so here at UC Davis, there's a serious effort to take this technology and to first of all try to understand what it does and how it works. And then second of all, to see if we can optimize it and use it for treating human cognitive disorders, including, we do have a protocol that we haven't started to improve cognition in people with schizophrenia. And Charan Ranganath, who's a researcher a memory researcher at the Center for Neuroscience, and now Evan, who is collaborating with Charan and does recording studies in awake-behaving non-human primates, have two projects between them. The first that I'll describe of Evan's is basically to try to figure out what this stimulation is doing, where it's going in the brain, how it's affecting brain rhythms, how we might be able to read it out in humans, because we obviously can't record directly from people's brains typically in humans. And then Dr. Ranganath, and I have a little hand in this other study, is actually taking this. We've already managed to show that we can make UC Davis undergraduates smarter for an hour from a single treatment of 2 milliamps over the dorsolateral prefrontal cortex. And that's actually pretty good because they're pretty smart to start with. And we do plan to eventually to take this into patients, informed by the information that we'll get from Dr. Angelides' study. So actually, just to keep going, because I realize I'm using up all my time here. Basically, Evan, you can correct me for all my mistakes. It's so scary to describe somebody's research project and have them sitting right there in the audience. Essentially, what Evan is going to do is he's going to do TDCS. It can be anodal or cathodal. And he's going to record from the brain, and he's going to record EEG. And he's going to figure out where those electrons go, how they affect neural activity, how that is related to improvement on a learning task, and that's Evan's expertise, is in frontal striatal circuits that support different kinds of learning, and also how that neural activity is related to things that we can record on the scalp in humans that can be a potential readout. And he will explore different parameters and hopefully give us more of a kind of detailed and reliable roadmap that will allow us to then do human studies, directly seeking, without 5 years or 10 years of an effort by a pharmaceutical company to improve cognition in schizophrenia, something no drug has ever been able to do so far. And this will have relevance to ADHD, to autism, probably to depression, other disorders. Someone actually once made the analogy that perhaps in psychiatry we're at a point where cardiology was in the past, where cardiology was all about drugs for arrhythmias, and now it's all about just using electricity, actually. You don't actually give drugs for most of the arrhythmias, just give a little tweak of electricity. So it may sound a little crazy in science fiction, but so did optogenetics and so did clarity just a few years ago. So I think we have to be open to the fact that we might be going in a new direction. All right. Now, one of the challenges with TDCS and related kinds of neurostimulation is that mostly they focus on the cortex. Now, it's possible that TDCS goes much deeper than that, and Evan's going to be looking at that. But you are probably aware that for certain severe neurological disorders, as well as severe forms of depression and OCD, there's a procedure called deep brain stimulation. where the circuits that are involved in regulating motor activity or regulating mood are stimulated directly. These are people who have just not responded to any medication treatment or, other forms of treatment, and they have electrodes. And for Parkinson's, it's a miracle. You turn the electrode on and you turn the stimulation on, and people's tremors go away, at least for a substantial amount of time. This is done in depression, it is done in OCD, but it's very invasive. It's never going to become a widely practiced treatment. But if we had another way of getting to those deep brain structures that was non-invasive, we would be really interested in using it. And Kathy Ferrara, who's an amazing bioengineer, she's a member of the National Academy of Engineering. She's a brilliant engineer who's also interested in brain health, basically has an experiment, and there are other people working on this as well, using ultrasound to go deep into the brain and to stimulate key structures. And this is in many ways quite similar to Evan's study, but this is going to be done in rodents. And instead of directly recording neural activity, she's going to use the MRI scanner and the bold response to read out changes in the deep brain that are being stimulated using ultrasound in a very highly anatomically constrained way. And so the idea here is that for some disorders, and they might be neurological ones or they might be psychiatric ones, where you have to get into these deep limbic structures that are not accessible through electrical stimulation or magnetic stimulation or other kinds of stimulation, you might be able to get there using ultrasound. So there's a theme here on technology, and actually I'm going to end on that. It's not that we only do tech here at UC Davis, but health technology is a big strength, and we're just building on our strengths. So the last project that I'll tell you about is a cool one. I showed you a picture of Tara Needham earlier. This is a study that was funded by the Robert Wood Johnson Foundation and involved a partnership with a startup company. And essentially what this is about is, let me go back. It's about using a smartphone app as an add-on tool. Basically, this is an app. It goes on your smartphone. If you don't have one and you're in the study, we give you a phone. That's a big incentive for these guys. And then we do two things. We do passive monitoring of things like sleep, number of phone calls, number of texts, activity, overall level of activity, and then we actually have them fill out several times a day ratings. How are you feeling? Have you been having conflicts? Are you taking your medication? And then we do all sorts of other stuff as well. So we relate that to things we can measure in the laboratory. And then what we also do is we have a real-time dashboard on the clinician's desktop that provides them with real-time information about all of these things, plus alerts. So if the person says they feel suicidal, there's an alert on the dashboard. If a person says they didn't take their medicine or they're not going to take their medicine, there's an alert that appears on the dashboard. More than a number of times, this has had a dramatic impact on clinical care. Tara's interested, so the main purpose of this study was actually feasibility. Can you take young people? And if you don't know about our clinic is for young people with psychosis. So these are people who are paranoid. Some of them are afraid of the internet. It was a big question as to whether these young people would be willing to participate in a study like this. And I think what we've found is not only are they willing, they really, really like it and they want to keep doing it after the study is over. And they're much more honest with their phone than they are with their doctor. Very interesting kind of new direction. Again, it's kind of tech, but I think very exciting and very innovative. And we funded, Dr. Needham already had this started up, but we funded an expansion into a couple of the neighboring counties and also an expansion of the kinds of things that she's measuring in the hope that we can kind of add this new dimension to mental health care. So there's this idea right now, some of you are probably wearing your Fitbit. I have mine on. I really like the Fitbit. It's been really cool. They call this the quantified self. And this is the quantified self in mental health treatments, is a quantified mental health treatment, something that's really been missing from our field. Okay, so, all right, I don't know if I have time. We have to finish, Fred. I'm going to skip. I'll just tell you.